Okay, hi everyone. Thank you for your patience. Sorry about that. I'm John Toman. I'm a senior technical fellow at Certora. And the talk I'm going to be giving about today is about a new technology that we've been developing for the past year or so around verifying LLM-generated code. So a bit of context, actually, before I get into discussing the technology, sort of what is the reason for us to be wanting to use LLM to generate code in the first place. And to do that, we have to talk very quickly about the Certora prover. This is our flagship technology. It's a symbolic reasoning tool that can formally verify smart contracts written in Solidity, Viper. We have support for Solana and several other blockchains. This relies on something that's called static analysis of memory and storage, how the smart contract is accessing dynamically allocated objects, how it's interacting with the state variables, and so on. Now, if you've ever programmed in Solidity, you've almost certainly heard of this feature, inline assembly. And this is a very frequently used and also abused feature, which lets you write low-level assembly code. And I'd actually say Solidity is almost unique in its the way it makes it extremely easy for you to write low-level code like this. Now, this frequently causes issues with our static analyses. And this is a representative example. It might be a little small, but this is a safe transfer function that we took from the Solati library. It is heavily optimized, extremely gas efficient, and this is performing just a transfer from, accounting for the fact that sometimes functions return false, sometimes they don't return anything, but all of this is doing it in an extremely gas efficient way. It's also absolutely galaxy brain in its implementation. It does things like overwrite the free pointer, but then put it back, trash other bits of memory, but then make sure to put it back into place at the very end. And I'm not trying to pick on Solati. Like I said, it's actually quite galaxy brain. It's quite intelligent, but it's also very representative of a lot of the inline assembly that you'll see out there in the wild, both when you're reviewing code or auditing code. And so it's not just a problem for our analyses. I claim this is actually pretty hard for you to review if you're not a frequent galaxy brain user. And so the question we found ourselves asking is, could we automatically generate equivalent implementations? Again, for auditing, code review, R static analyses, whatever. Now, the key thing here to notice is the automatically generate and equivalent. They're the two key parts of this problem definition here. And to focus on automatically generate is currently the year of our Lord 2026. So when you want to automate anything, you of course throw AI at it. So let's take this code, throw it into some LLM with a prompt that says, hey, rewrite the code using standard Solidity instead of inline assembly. Please make sure it's right. And then out will come something. You'll definitely get something out of the LLM. So great. Here's our system diagram. Just throw something into the LLM, get some simplified Solidity out. Is it this simple? And the answer is no, of course not, right? AI powered means you're getting AI powered mistakes. Right? And so this is actually one of the attempts that we got out of one of our test runs, simplifying this code. And the question is, are these actually equivalent? It looks very plausible, which the results of LLMs usually are. They look very plausible, but in fact, they are not equivalent. And the reason is this little sort of innocuous looking ABID code here. Now, the fact that there is a error here is not surprising. After all, the LLMs themselves are very quick to tell us that they can make mistakes, right? And so for us to just blindly put in code here to an LLM, ask them to rewrite it, and then trust the results would be utter foolishness. So what we actually do is we use LLM to generate code, but we add guardrails. So in particular, we take the original code in a prompt, which effectively just says, please rewrite this code to make it simpler. We then take the original code that we asked to simplify and then feed it into Concord. Now, this formally verifies whether or not two smart contracts are equivalent. And we'll get into what equivalent means later. That was the second part of our definition there. And if they are actually equivalent, then we return this to the user and say, yes, the LLM did a good job, and in fact returned a completely equivalent code, and here you go. If not, we actually get an explanation explaining why the two behaviors are divergent. We feed that back into the LLM, and this loops. If you're familiar with something like a Ralph loop, this is kind of similar to that, right? You keep iterating with the LLM, telling it got it wrong, and ask it to keep fixing its mistakes. And so this whole area between the two dotted lines are what we're calling concordance. This is an automated rewriting tool that uses LLMs to generate rewritten code. Now, again, I've been sort of writing this check for a while, and it comes time to cash it now, which is that we have this equivalent. And so what does it mean when we say the two contracts are equivalent to one another? Well, I will start with sort of an intuitive definition that I think we can hopefully all agree on, which is that two contracts are equivalent if they do the same thing on the same inputs, right? Now, of course, there's a lot to unpack there. So, we can sort of wave our hands here and have this diagram that says, equal inputs go to equal outputs. So I would try to make this a little bit more precise by saying that an external actor shouldn't be able to tell the difference between your two implementations. If you're just looking at the results of executing the smart contract on, say, EtherScan, you should never be able to tell the difference between executing one implementation versus executing some other implementation. The effects that they have should be the same. Now, I just mentioned effects, right? Because in addition to the actual explicit inputs and outputs, the values that get returned by the function, there are also state changes. Balances get moved around, ether gets moved, so on and so forth. Another word for this is side effects, right? And so when we talk about do the same thing or the same outputs, that also has to include this notion of side effects or state changes. So what are some of these side effects or state changes that could be included here? Well, I just mentioned one already, which is mutating storage. If you change the balances field of your pool, that is a state change. If you are emitting a log, that's a state change. That's something that an external actor can view. You can see that if you open up the execution of your smart contract on EtherScan, you can see the logs that it emitted. Calling another contract, and this includes both contract creation, balance transfers. That is another way that an external actor can observe differences in behavior. If you ever call out to a different contract and you're passing different balances or you're passing different arguments, that's an observable difference. So self-destruct is also there, but deprecated, so we're not going to talk about it ever again. So what are some examples of not side effects? Well, mutating memory and pushing and popping the stack. Now, again, these sound like side effects. After all, we're mutating memory. We are side effecting memory. So why do we not consider these side effects? And that's important because I was very careful to say external actors. The stack and the memory are not visible to an external actor, except to the extent that they influence the actions on the right. If you can push pop the stack 100 times, so long as you end up returning the same value, it doesn't actually matter to an external actor, except for wasted gas. And that's something else that we don't consider to be a side effect, which is the gas consumption. Now, that is a very real side effect. The amount of gas you consume will determine how much money you're spending to execute your smart contract. This is a practical trade-off we had to make because if we insisted on equal gas consumption, that effectively constrains your contract to be exactly the same, right? Just the chances that you'd have a different implementation that has exactly the same gas consumptions, just that admits only one implementation, which is the original. So we ignore gas consumption. So a final sort of more formal definition of equivalence is two contracts are equivalent if on the same call data in the same environment, they both revert with identical return data buffers or return with identical return data buffers and emit the same logs, make the same external calls, and end with the same storages. So finally is the actual equivalence checking itself, right? We've now defined what equivalence is. How do we check this? Well, this is actually just an application of the Certora prover, which I told you was a symbolic reasoning tool. What this can do is basically take mathematical expressions that assert some property about smart contracts and determine whether they exist or are the equation holds on all possible inputs. And so what we can do is encode equivalence as equality of side effects and equality of return values, and then verify this mathematical property. And so to see how we do this in an extremely high level and hand-wavy way, we basically separate these two things into two tuples. The function has its explicit output and then its implicit outputs, which are the effects that it has. We encode this as math by using math symbols, and then we check this with the Certora prover. So this is a 50-minute talk, so I'm not able to go into a huge amount of detail here. So I've hand-waved a lot of how this works. There is a tech report that you can go into. It's a 25-page document that goes into all the detail you could possibly want about how exactly this works and how this integrates with the prover pipeline itself. I should say that this is slightly out of date. Since we actually wrote this document, we've added support for loops, where we can actually now inductively prove that loops are equivalent, which gives us greater reasoning, modular equivalence, and things like that. Happy to talk afterwards if anyone's interested. So quickly, to give you some idea about where this has been successful, I said we use it for verified rewriting. We can also use it in other contexts, like verifying compiler optimizations. And in fact, using Concord, we were able to independently discover a bug in the Viper experimental code generation pipeline. There was an optimization that caused it to completely trash the local state of variables, and Concord actually managed to detect this and say that, hey, the behavior is diverging here because the optimization pipeline did something wrong. So quickly to wrap up, this feedback loop requires this explanation, and I want to give a quick intuition for what this looks like. So Certora Prover uses SMT solvers. These can give a concrete example, not just telling you that, hey, they're different, but why they're different. What did they do differently? And so to return to our example, I told you this ABID code was the reason that this was not actually equivalent. And so it's actually, this is the explanation we get out of the SMT solver. It says, what happens if the contract you're calling transfer from on returned 2, like 00002? Why is this a problem? This is not a valid encoding of a bool. A bool is either 0 or 1. The original implementation will just revert with transfer from failed. However, ABID code on malformed input will revert with an empty buffer. And this is the sort of nitty-gritty nitpicking that Concord is able to reason about. When we told the LLM about this, it suggested doing this instead, which gives the original behavior from the Solati implementation. So so far I've been talking about this to use LLMs to simplify code, but of course, as I hinted, you can use this by simply tweaking the prompt a little bit, optimizing code, porting code between different languages or frameworks, and so on, refactoring. And I should also mention it's open source. And I think, oh, that says wrap it up, and I'm done. So thank you so much for your time. Any questions? Yes.